this is important. The process by which something goes into solution, and in this case solids, the process of for example, turning salt into salt water, is called dissolving. And most of us are familiar with that process. When we make Kool-Aid, or when we make rock candy, or if for some reason we make salt water, we're dissolving salt into the water. The opposite process, where those solids come out of solution, for example, when salt water evaporates, it leaves behind what? It leaves behind salt. Or when water evaporates in your bathtub, or on the faucet in your kitchen, it leaves behind salts, actually. We call that the bathtub ring, or calcite, because all water, even the freshest of waters, or what we think of the freshest of waters, have a few minerals in them. So when the water evaporates, those solids come out of solution. And we call that process precipitation. A solid coming out of solution, salt coming out of water as the water evaporates, is known as precipitation. You know, we also use that word for rainfall, but we're talking about two different things completely. Now, as I said earlier, the substance that's dissolving, that does the dissolving, is a solvent. So, in this case, of salt and water, water is the solvent. The substance being dissolved is called a solute. And those are words that I use throughout the semester, and it's a good idea just to have a handle on the difference between those two. Water puts things into solution, well, by surrounding it. And here's a figure from your book. In this case, we have a salt crystal. Salt's made up of, as you know, sodium and chloride. Those are the basic components of table salt, and really of all of the salt that you find in the ocean as well. And when water dissolves salt, it actually surrounds the chloride atoms and surrounds the sodium ions. When this goes in water, chloride forms a negative ion, which we call an anion, and sodium forms a positive ion, which we call a cation. So water acts to dissolve substances by surrounding them and keeping them held in suspension in the water. Now, a common misconception that students have, and really probably most people, is that if you dissolve something in water, that eventually it'll just fall out. But that's not true, because salts aren't like sand. Sand is not soluble in water. Water doesn't dissolve sand. But water does dissolve salt. And when it dissolves that salt, it'll hold it in solution forever if the temperature doesn't change or if we don't evaporate off the water. So when something's dissolved, it's there. It's going to stay that way forever and ever until some conditions change. So keep that in mind. It's not like pieces of sand that are being held in suspension by the water. Water really interacts with those ions and those elements to dissolve something and keep it in solution. An important point. Well, here's a little joke, and you can read this in your book, but it will help you understand a little bit about salts. Another important term that we'll run into in future chapters is something called the saturation concentration. And the saturation concentration is really how much you can put in something. For example, again, if you were making, say, rock candy, those of you that are familiar with the process of making rock candy know that the first thing you do is heat up the water. Why do you heat up the water? You heat up the water because you want to dissolve more of the sugar in it. When you're first starting to put, in this case, salt, but it could be sugar as well, in water, that water is undersaturated with regard to its salt or sugar content. When there's just as much as it can hold and it can hold no more, we call that saturated, and that's the saturation concentration. So again, the amount of a particular solute, sugar or salt, that can be dissolved into a solvent, like water, that maximum amount is called the saturation concentration. Once we reach saturation, it doesn't matter how much you stir it or shake it or put more in, it's just going to settle at the bottom of your flask or glass or pitcher, whatever you're making it in. However, if you heat it up, if you raise the temperature of a solvent, you can add more to it. So raising the temperature actually raises the saturation concentration so that you can actually add more to it. And really, that's the principle of making rock candy, because what you want to do is supersaturate that water, hot water, you put the string in it, and then as that solution cools, the sugar crystals form on the string and create your beautiful piece of rock candy, right? Okay. Well, in seawater, we basically divide it into a number of different important ingredients. And we're going to talk about these ingredients again throughout the semester. So it's important that you kind of get these in your head and know what these terms mean. The major part of seawater, those 11 or 12 elements that I referred to earlier in the periodic table of the element, those are called major constituents. Their concentration is greater than 1 part per million. And you should get used to seeing this little acronym ppm, which stands for part per million. Major constituents. Concentrations greater than 1 part per million. Minor constituents, sometimes called trace elements, have concentrations less than 1 part per million. And as it turns out, anything that's not a major constituent is a minor constituent, of course by definition, but seawater really holds just about all those elements in some concentration. All the elements that we looked at in the periodic table of the elements can be found in seawater, even gold. And it's been said that if you were to mine the gold, you could be a very rich. Mine the gold in seawater, you'd be a very rich person. Of course, the money to do that would cost more than the worth of the gold, but you'd have a lot of gold. A really important group of compounds that's often overlooked in certain textbooks are what I call biologically important nutrients. These are those few nutrients that I talked about earlier, the ones that are important to microbes, like iron and nitrogen and silica. Those kinds of things are really important, so keep those biologically important nutrients in mind. These are things that are not only required by those microbes, but mostly by a group of photosynthetic microbes known as phytoplankton. And we came across that word once before, but if you remember anything at all in my class, and if 80 years from now you're thinking back on my class and trying to remember what you learned, remember this word, the phytoplankton. They are, to my way of thinking, and arguably, the most important organisms on Earth. Phytoplankton give us oxygen. That's what we breathe. About every other breath we take comes from the ocean, from the phytoplankton in the ocean. Phytoplankton moderate our climate. They control carbon dioxide in the atmosphere. That's what keeps us from being too cold and also from too warm, although humans are playing a role in that too. Phytoplankton also feed marine food webs, and that food happens to be the most important protein on all of our planet. More people depend on fish protein than any other protein in the world. So phytoplankton are important. They feed us, they let us breathe, and they provide us warmth. I'd say that's a pretty good friend. The other group of compounds that we're not going to talk too much about, but I just want to mention because they're getting a lot of attention in oceanographic research in the 21st century, are what we call dissolved organic matter, or DOM. And it's a fun word to say, so you might want to just practice saying it to somebody. DOM, 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 dissolved organic matter. This is the kind of stuff that you really are making when you make a cup of tea. That colored stuff in the teacup that you see, that those substances that leach out of the tea bag, they're really dissolved organic matter. And if you've ever been back east and seen a river, or if you've ever seen a lake that has a kind of a tea color to it, it's the dissolved organic matter that gave that lake or that river its tea color. And dissolved gases, and of course carbon dioxide and oxygen, are very important in the ocean, and we want to talk a little bit about them.